A lot of this is going to look very familiar. A lot of the start of these sort of Jupyter notebooks or Python programs are going to be the same. At the beginning, you're always going to load in some modules, and then you're going to start doing things. So the idea with this second exercise is to access the same kind of data, or this long time series of data, but instead of just choosing one point, choose an area. So if that's a square, or if that's a watershed, or if that's the boundaries of a city, or the boundaries of a country, or a state, or a town, any sort of geographic area that you want, you can also do the same kind of analysis and make time series from. So let's get into this. The data source that I'm going to use for this first part of the example is the ERA5 climate data. So this is a climate model data set that I guess they've run it from the 1940s until now, basically, and they're constantly updating it. I think it comes maybe 2 months behind the present day. So this is a really big climate model that they have lots and lots of different variables. So if I go to, let's see, ERA5. So if we look at this data set, we can see on Earth Engine, we have it from 1950 until basically 2 weeks ago. So actually quite a lot faster than I thought. And from this, we have lots and lots of different variables. So not just rainfall and things like that, but also dew point and skin temperature, soil temperatures, all sorts of different variables. So ERA5 is basically a whole Earth climate model. So they model from, I think, a couple meters down up all the way through the atmosphere. So they have lots and lots of different variables here. So what we want to do then is use some geographic data and pull in some of this data into certain areas. So I'm using these same few start modules, but I added a couple of extra ones. One is GeoPandas. So this is basically just a geographic extension of pandas, which I just showed you. So anything that is in tabular Excel data, but also has geographic information. So for example, if you have something that looks like this, but it's a list of rainfall station locations that all have a name and a date last serviced, something like that. So if it's a tabular data like this that has a geographic component, GeoPandas is the nice way to access it. And then we just have one or two other little utilities that help us turn this sort of shapefile or other common geographic data into something that Earth Engine understands. So we can run these again. And notice that I don't have the authentication thing here anymore. Since hopefully in the first exercise, everyone managed to create this token. Once you've done it once, you never have to do it again on your computer. Unless you reinstall your operating system or something like that. But now that you're set up, you should be able to just run it like this and quickly import things. So just to check that it all works, I'm again doing this same Mount Everest elevation check. This is actually what they suggest in the Google Earth Engine documentation as their make sure everything is working. So we can talk here for a minute about study areas. So I am using the outline of the Trishuli. This is also data that I put on the GitHub. It is here under geodata, this Trishuli GeoJSON file. But you are welcome to use any sort of watershed outline or other city outline, whatever you want to use here. So if you have a shapefile for your study area, or if you have a bounding box or something like that, feel free to put that in instead of the Trishuli. There are quite a lot of different ways that you can also create your own area. So for example, here in this document, I have a link to this website called geojson.io. Oh, it should. Well, we can just open it ourselves, geojson.io. Let's say this. So when you open this up, it just has basically a view of the Earth. But what you can do is you can choose a location. So for example, let's zoom in here to Nepal and say, okay, I'm interested in this area, or draw whatever you want. And it will directly pull up the coordinates in this kind of machine readable format. So this is basically this JSON format, which is something that you see a lot in web development or other things like this. It's basically structured data that the computer is good at knowing how to use. And just like we had before with the, we could go into Google Maps and right-click and copy and paste out that latitude and longitude. We can also take this directly from this website and use this as a input for Google Earth Engine. So if you copy this and open a text file, you can just copy it in. And this is already a GeoJSON file. This is already something that Google Earth Engine can recognize. So if you don't want to open up a GIS software, if you don't have a shapefile or something like that, you can just go and you don't have to just draw a box. You can also draw something more complicated around a reservoir or a lake or something else like that and get these coordinates. And now you have this thing. Maybe I'm just going to save this somewhere. Let's put it in my geodata as test box, GeoJSON. And then we can load that in a minute and make sure it works. I think also with this GeoJSON file or the GeoJSON website, you can open up another file. If you have a shapefile and want to convert it, you can open up a shapefile here and get this out. You can also, instead of doing this copy-paste thing that I did, I guess you can also save it directly as a GeoJSON. I always end up copying, pasting things, but this will also work if you want to save it as a shapefile or as a GeoJSON. So this is a really nice way, rather than opening up QGIS or something as ArcGIS, to quickly make a geographic area. So once you've made a study area, to load it in to our Jupyter Notebook, we just use this one line, which is GeoPandas, and it reads a file. So it will read any shapefile, GeoPackage, GeoJSON, I don't know, what other geographic files you can think of. Anything that has geographic information, GeoPandas can usually read. And it will, in this case, so I have my Trishuli thing, which gives me basically all the attributes that I have in my data set, and then this big set of geographic coordinates. I can also, maybe I'm going to make a second one so we can just look at this test box, call it test outline, and I will open up this test box. And this, since I just drew it and it doesn't have any extra attributes, right? I don't have a name or something else like that. It just has my geometry. But it has exactly these coordinates that I put in from geojson.io. So it's pretty quick and streamlined if you want to open up this kind of file, even if you just make it on the fly or want to change it from day to day, something like that. All right, I'm seeing that some people have created their own outlines, and you can name it whatever you want. So I named I'm going to go through the exercise using this. and I'll also show some of it with my test outline. So if you named this something different, then just remember that's what I'm calling it. We'll come back to it when we start using it. So in any case, with any of these outlines that you load in from your own shapefile or copied from this GeoJSON, Google Earth Engine doesn't understand it directly. You have to convert it into this format that Google Earth Engine understands, which is very, very close to this JSON, but not exactly. So this is what this line is doing. I'm just using basically this mapping thing that we imported to turn this into something that Google Earth Engine understands. So when I run this, I'm again doing this area of interest get info. So I'm getting the actual parameters here, and it gives me something like this. So this looks a lot like this, right? It's almost exactly the same, but it has one or two small differences. Like this just says polygon and then coordinates, and this says features, then feature, then coordinates. It's like the smallest difference, but it won't, Earth Engine won't directly recognize this. So this is why we have to do this very small sideways thing to turn it into exactly what Earth Engine knows how to do something with. But once we've done this, we have our area of interest. We can do any sort of spatial operations on Earth Engine. So clipping out data, doing averages over a space, etc. So maybe just since we're right here, I'm going to make a second polygon. Let's just copy this, and I'm going to call it area of interest number 2. And instead of Trishuli outline, I'm going to call it test outline. And that now I have a second one that is just that small box that I made, just so we can compare these two different ones and see what they both look like. So ERA5 data, as I showed you before, and we can open up one of these links again, there is a lot of different data in here. And these different data sets also have different time ranges, right? This daily aggregated data goes only from 1979 to 2020. And this other one that we looked at before, this somehow differently daily aggregated, is 1950 to 2024. So there's a lot of different ERA5 data sets on Earth Engine, and they all have slightly different variables. So for today, the ones that we're going to do is the simplest ones, the ones that go only from 1979 to 2020, because that's long enough for looking at some climate trends. And this has a smaller subset of the variables. So it only has mean, min, max temperature, dew point, precipitation. So it doesn't have all these different pressure level things. So if you're looking for more atmospheric analysis, then these ERA5 land data sets go into more detail. But for us, for just this surface data, we're just going to look at this ERA5 daily data. Because there have been a lot of days since 1979, it's a really, really big data set, which means that it can be kind of slow to export time series or do these kind of big aggregations, right? So there is also monthly data, and I also put in here hourly data. So ERA5 data, they do, I think, down to the 15-minute resolution. Earth Engine has hourly data as their smallest time period. So depending on what kind of analysis you want to do, maybe monthly is fine and you can do it really fast. Or maybe you need daily or hourly data, and then you have to use a smaller area, basically. You can't get as much data. If I run this, I'm just going to load in my 3 data sets. And just like we did before, I'm going to get the size. And I'm just going to print these 3 sizes, just so we can get an idea of how much data is different, or how many different data points we have for hourly versus daily versus monthly. So it's a really, really, really big difference, right? The difference between working with 500 data points and 650,000 is quite large. So if you want to make a plot like the kind of rainfall charts that we were making, trying to make a chart with 650,000 points on it is going to be tough. It's going to be really hard to understand all the small changes, and your computer is not going to be happy with you anyway. So I always think of what is the smallest time resolution that I need? Can I get away with looking at trends only on monthly data, or do I really need daily data? So all of these different things are accessible, but generally you want to choose your data set based on what your question is. So if monthly data is not helpful, then you have to try to use daily. If monthly data is fine, stick with monthly data. It's going to be a lot smaller and faster to work with. So for this example, I'm going to take my own advice and work with the monthly data, just because it will be a lot faster for us to run through these analyses. But if you want to change, if you want to do the hourly or the daily data, you can use exactly the same code that we're going to use here. You just switch to use the hourly instead of the monthly data, and it will do the exact same analysis. So you can try to run this with the daily or the higher resolution data and see how much longer it takes. Don't worry about how much bigger this is. This is basically the exact same thing we did this morning, except I added a mean, a maximum, and a minimum. So we're no longer looking at just one point anymore, right? So if we're looking at a big area, then it's useful to not just have the average precipitation or temperature, but also what's the maximum every month and what's the minimum every month. So I just extended this function a little bit again. So we get our date in the same thing as before, but now we have a minimum, a mean, and a maximum. And I'm going to talk a little bit more about these functions in the third exercise a little bit later. But otherwise, then we get our time series, and I'm converting it just in the same way. So I just put it all into one package. So I'm going to keep making things smoother and smoother. We only have to run one function instead of running 2 or 3 cells to get to the same thing. So what this will do is I can put in my monthly, or if you want to try, you can put in daily. Then your area of interest, or the area of interest number 2, if you want to get that one. And then the variable I'm interested in right now is total precipitation. Of course, if we look here, we have other options as well, right? So if you want to look at the air temperature instead of total precipitation, go for it. All you have to do is change that one little line right there. If you change this to temperature, then you're going to get temperature instead of rain. But again, the process is going to be just the same. So I guess here is where I put my note about what kind of math we're doing. And this then refers back to these things here. So these 3 little pieces here. This is what's telling Google Earth Engine what kind of math I want to do. Do I want to take the maximum? Do I want to take a minimum? Do I want to take a mean? It's this reducer. How do I want to reduce my big collection of data into one value? And there are a lot of different reducers. There's standard deviation, there's variance, there's even trend, there's all sorts of things. Any kind of analysis that goes from many data points to one single value, they have probably 100 of these things that you can put in there. So this is also very flexible. If you're not interested in a mean, but rather in a slope or a relationship, you can also put that in the same kind of way. And I'll show you how to do that at the end. We'll look at some climate trends. So now that I've run this, I again have now a big set of dates starting from 1979. I also have some means. So these are my monthly mean precipitations for each of these individual months, right? Since I'm looking at my monthly data. And this is averaged over my whole catchment. So just like before, it only took a minute or two to create all this data, and I could plot my minimum, mean, and maximum over the whole catchment from 1979 until 2020 for every month. So that's quite a lot of data, right? And it's pretty easy to access. And it's quite flexible if you want to do a different kind of aggregation. But since we're looking at sort of spatial data, right? Data that's over a whole area, it's also nice to put that on a map. I always think before I look at the time series, I want to look at a map. So we can also do that from Google Earth Engine. I guess I got to zoom in a little bit more. One more thing first. You can also then, of course, look at something like monthly differences. So if you have your maximums and your minimums, you can look at the monthly temperature range for each month and see that somewhere in the 90s, there was a period where the temperature was pretty stable month to month, and then most of the time you get these high ranges, I guess, in the summer, and these low ranges in the winter. So this would be potentially like a weak monsoon time when there wasn't a huge difference between the min and the maximum precipitation per month. So let's then try to put some of this on a map. So in the same way, it's exactly the same kind of, the same thing here, right? This reducer thing, taking lots of data and making it one value. What we did here to make a time series is we reduced all the space to one value per time. But we can go the other direction as well, right? So if you have a lot of different times and you take an average over time, then you get one value per each space. So basically making a map of a long-term average value or a long-term maximum value, or just the value for every year, something like that. So instead of making one long chart, we can make a map. And that's the idea. So we're going to use the exact same value, but instead of doing this whole giant turn into time series thing, we're just going to use a reducer which defaults to reducing by time. So if I do reduce mean, this long-term mean is now just going to be a single image grid. It doesn't really give you very much information about it. It just tells you that you have a total precipitation mean and that it's an image. And that's it. That's the whole command to create this image. And we only have to run one more command to, well, I guess first we can try to visualize it. This line, everyone tell me if this works or not for you. Some people this works by default, and some people you have to run this extra command to turn on an extension. Basically what this GEE map module lets you do is it lets you make a little web map. So the same way when we were going around in this is a small web map. So you can do the same thing within Jupyter and plot your data. So here is my long-term precipitation. Oh, it's a lot darker here than it is on my screen. But this is the result of that calculation that we just did. This is the average of all the monthly precipitations for the last 40 years. And maybe I'm going to just run it a second time so we see how fast this actually goes. Right? That's pretty quick to come up. And you can zoom around in this and take a look. This is exactly now also where you can start seeing what the grid lines are on this data. And you can also, just like in the first thing I showed you with this introduction, there's an inspector tool. So you can click on one value and get the actual average out of that individual pixel. Though mine is going a little bit slow here. There we go. I guess everyone is on the Wi-Fi at the same time trying to do this. Oh, my Wi-Fi just died. Here we go. All right. So where we left off, I saw some of you managed to pull this up, and some of you were just seeing what's possible and not stressing so much about actually doing it. Like I said, we're going to be recording all of these, or we are recording all of these, and we're going to put them all up on YouTube, as well as all the materials on GitHub. So if it all ends up being too fast and you just want to see what's possible and then go back and spend some more time on your own, also fine. This was just showing how quick it is to quickly visualize and actually run on the fly these long-term means. So this is the precipitation average from ERA data. And you can see even if I zoom out, it should pretty quickly start to fill in this map. And it's just doing this on the fly, right? And this is 40 years of data. So this is a pretty powerful thing that we're having Google run for us and just send us back the small bit of image information. We can, of course, also do different calculations. So instead of a mean, we can get a maximum, which I will skip there just to go on to the maybe more interesting thing, is that we can also do trends, right? So looking at climate trends is something that I'm sure a lot of you are interested in your work and your studies. Just the same as we're doing this reducer to do a mean or reducer to do a maximum, you can also take a trend. So take all the values on one point and get the trend over the last 40 years. And you would think that this would be a lot slower, right? Doing a trend is somehow more complicated than just taking a mean, but it goes pretty much the same speed, right? So that in that couple lines of code there, I can get the rainfall trend over high mountain Asia for the last 40 years. And this is something that you can, of course, zoom around in and look and see that this red stuff is where there's been a bit less rainfall, and the blue is where there's been more. Yeah, so this is just a nice, quick way to visualize this. We can also, just for comparison, do the same thing for air temperature. So I'm using this same little time regression thing that I just made, but instead of doing precipitation, I'm doing the mean air temperature, just so we can compare them and see that this is probably as expected, pretty much all red, right? Temperatures have increased pretty much everywhere. And they've actually increased more than in other places in exactly these high mountain regions that a lot of us work in. So let's do one last thing, and then we can move on to the third exercise, which is focused on making nice maps, which is once we have such a data set, right, we can play around with our area and choose the data set, and we make a nice little web visualization so we can just move around and see what it looks like. But if you want to actually make a nice map out of this or send someone the data set, then it's good to download it as its own file. So working with it as a GeoTIFF file or some other kind of image file that I'm sure many of you have seen before, right? How elevation data or other data is sent around. Thankfully, we can export data. And once again, I've included a little function here that does this for you, that it just takes in an image, and you want to know the coordinate system and what you want to name it, and what spatial resolution, and for what area. And this will just run on your Google Drive. So this will just export to your Google Drive. If I look at there's this website, tasks, there. All of the different things that you want Earth Engine to export, so anytime you want to save data to your Google Drive, it should come up here. And you can see that I've done some other things for preparing for the workshop, but you can also see that it took less than a minute to export the trends for the Trishuli. Right? So we're doing a big long-term trend analysis on 40 years of data, and they can send it to me in less than a minute. So it's a pretty nice thing that you can get data pretty fast. And the data will show up directly in your Google Drive, which I hope I don't have too much stuff in mine. Yeah, I've got a lot of stuff in mine. But it should be here, this whatever I called it, the monthly mean temperature trend, and it's just an image file. And I can open that up, for example, in QGIS, which I'm sure some of you are familiar with. Where did I put it? In my geodata monthly rainfall trend. And that will just give me the part that overlaps with Trishuli. Maybe I should add Trishuli on here also. So that will just give me the pieces of the ERA data set that are exactly over my watershed. And maybe a little bit extra because it's making it a square box. So just to emphasize that and maybe do it a second time, I can also run this for whatever kind of area I want. So if I specify a different extent, so I say I want to go from 65 to 110 and 25 to 45, that's basically all of high mountain Asia, right? That's from sort of Afghanistan to, sort of the end of Bangladesh, a little bit into China, and from sort of the middle of India up until almost when you hit Russia, right? So it's a pretty big square. And I can just make my polygon, which is from the different corners, right? The minimum X, and then this corner, this corner, this corner. And I can run this as a large trend. And I'm just using the exact same data. And again, I can go look at my tasks. It should, if I refresh this, pop up. And we can see that even for this large area, it should only take a minute or so for this to run. I can probably look at how long it took last time I did this. Maybe not. Let's see. Total runtime, 10 seconds. And that will, again, be in my Google Drive. And I could open this up and look at it. And this is this trend large, which now covers this much larger area. So this is my rainfall trend, right? That took 10 seconds for me to export. This is a very nice example of why it's nice to do this kind of processing on somebody else's computer machinery, right? If we wanted to download this data and do this ourselves, it would take a lot longer. Yeah, and that's it for this second exercise. Are there questions on this? I know I went a little bit fast through this exporting part. We can look again, we'll look again at exporting in this third exercise. Okay, cool. Then let's